0 hours after exposure? Are you testing 1 hour after exposure? Or are you testing 3 hours after exposure? The same hypotheses. The hypotheses are, yes, lung function is reduced. No, lung function is not reduced. One of those two is correct. It's binomial. We just don't know what the probabilities are with the binomial. Very, very good. Much like the chickens. Much like the chickens, although the chickens, they tell me the percentage. 90% chance of a girl. We can test that. We actually will test that, because I got 4 more girls coming in to see if they're all female now. But the idea is here you don't necessarily have a percentage to work off of. So whoever told me to put 0 in for baseline, I love that idea, by the way, whoever said that, throw 0 in for baseline, that was great. Because if you don't have a number, then call it 0. And then build your curve around that 0. The important thing isn't so much the 0, it's how wide the curve is. And that's governed by your data. Now, what I want to do with the rest of this time is, I want to talk about the ways of being wrong. So I back up a couple slides. Now, we're kind of going a little bit out of order with you guys. I apologize for jumping around a smidge. Let's go back to the first conclusions, which were at 0 and 1 hour. We said that we were expecting secondhand smoke to have no lowering effect. But what the hell happened? We put them in a room with a box with smoke, we pulled them out, and what happened to their lung functions?
They lowered.
They lowered. So we were expecting no lowering, we got lowering. Is that a contradiction?
Yes.
That's a contradiction. How does the p-value show that it's a contradiction?
It's less than
It
5%.
comes in small. Yes, it comes in small. Now, one of two things can happen. Number one is the conclusion we came up with. And the conclusion is that, what does secondhand smoke do?
Lowers lung function.
Lowers lung function. That's one conclusion. What's the other possible answer?
Not lowering.
Right, but it doesn't look like it doesn't. But maybe we just got an outlier. Which means, could we be wrong? Yes, we could have gotten an outlier. What would we call that if we were wrong in this way? Use a 243 term. A false, it's a false positive. Why is it a positive test result? Why is it a positive test result? Well, that's why it's false, because we were wrong. We can also have a false negative. But why is it a false? It's false because we're wrong. It's positive because we said something changed. That's what a positive test result always does. It says something changed. When you go into the study, you're assuming that nothing's going to change. As soon as something changes and you flag it as change, it's a positive test result. Now you can be right or you can be wrong. You can be right or you can be wrong. So that's the way we can be wrong. It could be a false. We could have reported on 2 false positives. Maybe secondhand smoke has nothing to do at all with lung function. But we just got random deviant data, which happens 1 in 20 times, yes? That means we're wrong with a false positive. Put that in the back of your mind for right now. We'll come back to that. We'll revisit that with some fancy terms in a minute. Let's jump back up to the 3-hour mark. 3 hours. We were expecting secondhand smoke to have no lowering effect at all. And at 3 hours, what did we get? No lowering effect at all. That means this and this, do they contradict each other? No, there's no contradiction there. So how does the number of the p-value reflect the fact that there is no contradiction? It's big. It's big, yes? It's big. Big. Could we be wrong?
Yes.
Of course we could. We can always be wrong. What would that be? A false negative. Yes, that's a false negative. We haven't talked about these much. We haven't talked about this much. That's a false negative. That's saying, you know what? It's totally fine. After 3 hours, even if you suck out a whole bunch of secondhand smoke, your lungs are just fine. You might be wrong. You may have gotten deviant data from the other curve that puts you back on what appears to be the null curve, yes? So it's still an outlier, but it's going to be an outlier on the other curve. Please, Veronica, please.
Is it possible, though, that we could be close to the 5%, and so we did have reduced lung function,
I love
we
that
just
question.
can't show it
I love
as
that.
well?
How could... Can we maybe show it better? What do we have to
More
do?
studies.
Melanie's solution. Replicate, replicate, replicate. I have an entire homework question that's got about a 5-page solution to your very question. I'll point it to you at the end of the day today.
Okay.
It's what if you get a p-value close to 5%? What do you do? See, all they tell us right here is that they're less or greater than 5%. And students kept asking me, I'm like, you know what, that's a freaking awesome question. Let's dive into it analytically. What happens with close to 5%? The best thing to do, replicate the study. Because if you replicate the study, even if you get the exact same results, the p-value has to go down. Why would the p-value have to go down, even if you got the exact same results, Natasha?
Because you have more, a larger sample.
Yes! Because think about it. Suppose you get, I love what you just said, Veronica, about the close to 5%. Suppose you landed like right there. Damn close to 5%, yes? Maybe a smidge under, a smidge over, whatever. Suppose you think there's something going on, but you can't quite nail it with this. What do? As Melanie and Linda pointed out before, replicate. Do it again. If, and this is a big if, you get the same or close to the same results, that is going to park exactly where it is. It's not going to move, but this curve is going to do this, which means you've got way more area closer over here, which means the area here went down. That's the beauty of replication. Yes! Thank you for that question, it was fantastic.
Yeah.
But if you want to see it more kind of processed, if you look at the homework for this, and I'll point it out again later on, I've got it all broken down. It's a great question. And it's the essence of replication. It's the essence of weeding out outliers, if you think there's an outlier, because this will weed them out for you. Excellent. Let's get more into this way of being wrong. Because this is what we're going to end with this today. We're going to end with this today. Because this, Linda, you asked about this about an hour ago. I promised you an answer. I also promised to make you wait for the answer. I apologize for that. I want to make sure we get the p-values in the bag first. There are 4 ways an hypothesis test can end. A true positive, a true negative, a false positive, or a false negative. Obviously, you want to make the false's likelihood as small as possible and the true's likelihood as large as possible. And the only way to consistently do that is to get more good quality data. Proper. But I want to analyze this. Suppose you do your study and you get a small p-value. What do researchers do when they get small p-values generally? What kind of a dance? Happy dance. Why do they do a happy dance? Oh, sorry, Veronica. I just hear a female voice in this general area. Why do we do a happy dance for researcher when they get a small p-value? What does it mean? Good. Thank you, Lola. Statistical significance. The common response. Something changed statistically significantly. So whatever we were studying, the null hypothesis is almost impossible to believe now. We can't believe the null, which means something changed. So we got happy dance. Because then we can publish our results. Maybe we should. We can, by industry standards. But the problem is, there's a chance you're wrong. There's a chance nothing changed and you just got what? An outlier on the null curve. That's a possibility. That's the problem with these. That's a problem with probability. Is that it's not certainty, it's probability. So, the chance you're wrong in this class will always be 5% for a type 1 error. There's some language here. It's called a false positive from 243. In 244, for whatever reason, they switched that over to what's called a type 1 error. I agree with you, Linda. I agree, they shouldn't do that. Unfortunately, I'm going to teach you guys kind of the classic phrases as well as the more conversational ones. Just because that way, if you go to other statistics courses, you have the classical phrases, but you also can explain this. I always like to think of explaining this to your neighbor while you're out doing yard work together.
And that is a false negative.
That's false positive.
False positive.
Right, that's false. Why is it a false positive? Thank you. No.
Type error.
Type 1, false positive. Why is a small p-value associated with a false positive? Because you're saying something changed. If you say something's changed, that's a positive test result. It's like going to the doctor for Lyme disease and coming back positive. It means you go in assuming you don't have it, and the test says you do. Careful, careful. The test says you do. It might be wrong, correct?
Could be wrong.
Of course the test could be wrong. You analyze it in 243. As a matter of fact, the test is often wrong. It's a piece of crap test. Only test I know is I finally found the rings on my body and my Bell's palsy kicked in. I'm like, well, I guess I got Lyme disease. I'll take amoxicillin now, thank you very much. So that's the problem with a small p-value. A small p-value, now somebody said, who said earlier it's really small? The 1 in 1,000 was like really small, like even better than just less than 5%. It's less than 1 in 1,000. That was a fantastic statement. And if it comes in very often, you'll see in articles p approximately equal to 0. Because it's so small, it rounds to 0 to 4 or 5 decimals. That's pretty good evidence it's not on that null curve anymore. But there's always a chance it could be. So by definition, Veronica, go,
So
please.
we're just saying there's a possibility,
Of
or
course.
probability
Yes, ma'am.
that there's
Yes,
a
ma'am.
false
That's
positive.
all you can do.
Okay.
You can say it appears as though we got significant results different from the norm,
Okay.
but you admit that there's a chance we just caught outlier data and therefore we might have skewed results, and we encourage our colleagues to replicate. Encourage your colleagues to replicate. Just another historical side note here, quick historical side note. Fisher, the statistician, I forget his first name, something Fisher, he proposed a p-value. He proposed this whole idea of a p-value 100 years ago. And his exact words, paraphrase, I shouldn't say exact, but the spirit of what he wanted to do was the p-value is a second look. If it comes in small, you take a second look. It doesn't mean you publish your results and claim that we should all start smoking cigarettes because after 3 hours our lung functions are back to normal. It means maybe somebody else should replicate this study under similar conditions and see if the results hold. The true scientific method. Good, thank you, thank you. Okay, now this is where a type 1 error could have happened in this study. This is one of the places actually. At 0 to 1 hour, most lung function parameters were significantly reduced. Do you see why that's a positive statement? It's a positive test result statement. Because you're claiming that lung function parameters were? Changed. Good, thank you for that. You're claiming it changed. What I want you to do is, yeah, it could be a type 1, it could be a false positive. What I want you to do is, I want you to say what that means. Explain to your neighbor how the study could be wrong. How would you verbalize this type 1 error? You're out doing your yard work in the spring, beautiful day, it's going to be 81 on Thursday, according to what the weather says. 81, you're out there pulling weeds out of your garden, your neighbor comes out, hey! Did you read CNN this morning about secondhand smoke? Yeah, it looks like lungs don't work as well. Oh yeah, but they could be wrong. Really? Yes, it's positive, false positive, 5% chance of false positive. Your neighbor walks away, stops bringing you free beer because he works at the chutes. So how would you explain that type 1 error to your neighbor in context, in conversational context? I'll get you started. Because this is a bit of a tricky question. The study claims that secondhand smoke exposure lowers lung function, comma, when, comma, in fact, comma, finish it with a couple words.
There's a possibility of outliers.
Even simpler than that. The study claims secondhand smoke lowers lung function, comma, when in fact, it... Put one more word in there. You think it too hard.
Changed.
It didn't change. It doesn't, it not necessarily increase, it just doesn't lower. See, the study is claiming, you're thinking too hard about this, I'm sorry. The study is claiming lung function parameters are reduced. In other words, the study is claiming lung function went down. If it was wrong, that means lung function actually didn't go down. But the study claims it did. That would be a contextual interpretation of type 1 error. Saying lung function went down when in fact it didn't go down. That's all. Don't overthink it. I'm sorry.
They're kind of talking about their site, because it went down, then it went right down.
Right, no. Did it go down? They're saying it went down, but they could be wrong about that. You see what I'm saying, Linda? No, Linda, you have to make peace with this. This is not algebra. We have to make peace with the chance that everything we say has a probability associated with it. We're only 95% confident in our result. Remember that? That means it's a 5% chance of an outlier, which is a 5% chance that we missed something that didn't actually happen. So you gotta remember that. How many studies have you guys ever heard that have been overturned? It happens all the time, yes? That's because it was a type 1 error. They got outlier results, yes? They got outlier results, and they were overturned by further study. Remember the single child complex? Don't have a single child. If you have only one kid, that kid's going to have all kinds of behavioral issues and blah, blah, blah. Turns out that study was completely misdone 150 years ago and has been quoted ever since. It's been overturned a number of times. Type 1 error. Actually, that goes beyond type 1. That was just a crap study. But regardless, when you overturn a study, it's because you made a type 1 error in your initial study. Roughly 1 in 20 studies are going to get one of these, aren't they? By definition of 5%?
Yeah.
1 in 20 studies are going to get a type 1 error. So yes, the study, Linda, is going to say, and everybody for that matter, the study is going to say lung function went down. But there's a chance it didn't. There's a chance we just got deviant data, and that's what we're saying. The study said it went down when in fact it didn't. It's the same as it always was, we just missed it. It's a little bit heavy, I understand that. Not much math going on today, I apologize. We'll get more math on Thursday. But that's the idea, and I'm sorry for the frustration, but unfortunately every study can be wrong. Alright, let's look at a type 2 error. Which would be a false, what? This would be a false negative. Let's see if